watch a little video afterward. Ooh, this is greasy. I don't know why this feels like this. Science time. Today we're going to talk about light waves. What are we going to talk about today? Light waves. Froze. Oh, no, it didn't. I didn't press the button enough times. There we go. Did not freeze. Today we're going to talk about light waves. What are the two kinds of waves that we said in the very first lesson that exist in nature? What are the two broad categories of waves? Transverse and longitudinal. We had them like this. We had transverse waves that we diagrammed like this, which, just so you know, longitudinal waves can and often are represented in this way, but in reality, longitudinal waves behave instead like a series of compressions and rarefactions, as we talked about. Compressions of particles and rarefactions of particles. And they correlate, at least roughly, with the crests and troughs of a transverse wave. What flows in a wave? Remind me? Energy. Very good. Matter does not. Even in a material wave, which a longitudinal wave can be, and a transverse wave can be too, but even in a material wave, a wave where it's made of matter, the matter isn't moving. The energy is. The matter oscillates, but it doesn't move from place to place. So, transverse wave, and once again, there's no, it's not like light waves are this and material waves are this. There are material waves that behave this way. There are material waves that behave this way. But we're talking about today as light waves, which are a kind of transverse wave. Reminder, what is this distance called? It's called wavelength. And what is this distance called?
Amplitude.
Let's all try to answer the right way. Amplitude. Okay. Because we're going to talk about, oh, and sorry, the last thing is how many waves pass in a given amount of time, usually a second, is called the frequency. And so those quantities, those are the three measurable quantities of a wave, and we're going to talk about each of those in the context of light waves today. The general equation for light waves is C equals lambda nu. This is C, the Latin letter C, which you know as the letter C, but these are Latin letters. The letters that we use in our daily life are Latin letters. C equals, this upside down Y looking fella is called lambda, a Greek letter. It's a lowercase Greek letter, lambda. And this squiggly V, I kind of did a bad job drawing it, but what it really looks like, it kind of looks like it has a little tail, and then straight down, and then a curve, and that's the Greek lowercase letter nu. Nu. And so this is our general form for the electromagnetic or light wave equation, where C is the speed of light in a vacuum. Oh, I thought waves couldn't move in a vacuum. Didn't we say that last time? We were specific though. Yeah, which ones can't move in a vacuum? Which ones can't, when I say move, which ones can't transmit energy in a vacuum?
Water waves.
Water waves can't. Sound waves can't. Those are both kinds of what we had last time, which were, yes, mechanical waves. Mechanical waves cannot travel in a vacuum, but light waves, electromagnetic waves, can. So C is the speed of light in a vacuum. This is the Greek letter lambda. It's spelled like this when we spell it out. And this is the symbol for wavelength. The Greek letter lambda makes the ol sound, which is why we use it for length. At least that's an easy way to remember. I'm not saying, I don't know that to be true. I'm not saying that the word, whatever the Greek word for wavelength is, starts with ol, but the way I remember it is that this ol letter in the Greek alphabet stands for length. That's a mnemonic, not a definition. And then this, the lowercase Greek letter nu, is wave velocity. I'm sorry, that is not right. Wave frequency. Hello, Mrs. Lemon.
Mr. Kime, there's a basketball game this afternoon. We're going to have to postpone.
Okay.
Unless you want to do access.
No, we're doing quiz bowl and access. Thank you.
All right, thank you.
Nu is the wave frequency. Let's talk about what each of these are measured in. Frequency is measured in the unit hertz, which is just abbreviated Hz. And it's equal to the quantity 1 over seconds. Like the unit seconds, you know, like it's been 13 seconds since I ate a Twinkie or something like that. The unit seconds, 1 over that, let me rewrite this so it's a little bit more legible. The inverse of that is how we measure frequency. So what we're really measuring is how many waves pass in a given usually second. So however many waves pass in a second is that number in hertz. So if we had a wave that was 30 hertz, that means 30 waves pass in 1 second. Yeah, and that's really actually very, very low for an electromagnetic wave. It's even very low for a sound wave. Middle C on the piano, it would be very interesting to see if that's actually middle C. I very much doubt it. But that middle C on the piano is 440 hertz. So the air molecules are vibrating 440 times every second when you hear that sound. And then higher pitches for sound have higher frequencies and lower pitches have lower frequencies. And then wavelength we usually measure in meters or some variation of meters, as we talked about. For electromagnetic waves we often measure in nanometers, which is billionths of a meter. And the speed of light in a vacuum is, well, if we multiply meters times, let's do this little algebra over here. Algebra box. If we have this times this, you see where I got these values from? What did we end up with? No. This is this. This is the equation. It's not an equation. There's no equal sign. What is this expression reduced to?
Reduced to m over seconds.
Seconds, yeah. It's just meters per second, which is a unit of speed, remember from the beginning of the year? So meters per second. We usually use just an S to abbreviate seconds, by the way. Meters per second, which is a valid unit for speed, so we measure the speed of light in a vacuum in meters per second. And not only that, but not only do we have a known unit for this, but we have a known value. It is 300 million meters per second. Or, if you know scientific notation, 3.0 times 10 to the 8th meters per second. 1, 2, 3, 4, 5, 6, 7, 8. You've done scientific notation, I trust. Yep.
Why do you have to have 3.0?
Just, well, you could have it. You could have as many as you need to make it these digits significant. We'll talk about that when you're in chemistry, which will be in several years. But basically, the more zeros you have here, this is a side note, Garrett. Let's put another little side note box here. If I have that Garrett is 5.000000 feet tall instead of 5, are those the same number? No, they're not. They're mathematically equal because you guys are used to doing math. But if we're making actual measurements in the real world, what this tells me is that I have measured to the tenths, hundredths, thousands, 10,000s, 100,000s, millions, 10 millionths places. I've measured to 10 millionths of a foot and found that Garrett is exactly 5 point this many tall. Whereas this could be 4'6", couldn't it? And I just rounded. Since we do a lot of rounding in science, this means we only have one significant figure. It could be anywhere between 4'6" to 5'5", or I mean, it could be 5'5" and a quarter, and still be 5 if I just have this. But this tells me that I've rounded, or I haven't rounded. That's this precise. This is a measure of precision. Side note. Go away. Side note. Anyway. So 3.0 times 10 to the 8th, we've just measured it here to the 10th spot. The reason I wrote it like that is because in scientific notation, we always have at least we always have just a unit here, or sorry, a digit here, and then at least one decimal digit. Anyway, this is all how we describe electromagnetic waves. What do I mean by electromagnetic waves? What's the little abbreviation for this? I don't mean to. Yeah, EM is fine. But what am I talking about here? What's the layman's term for this? Electromagnetic waves are, as you read in your exploration, what? It's like the very first page of your exploration. Electromagnetic waves are
electric and magnetic.
They are both of those. Yes, that's true. But we abbreviate that as lay people. I'm going to say it, so not never. I would never in my normal life say, the electromagnetic waves reflecting off of your eyes is a beautiful color. Light. Yeah, it's light. This is light. We call them electromagnetic waves because in this case, these transverse waves, we could describe it this way. These y-axis oscillations represent electricity, and we also have pretend. This is supposed to be three-dimensional, so pretend it's going woo like this, but I can't draw that. I mean, I can't like get a 3D printer pin and then get a drill and make it go in. But pretend this is coming in and out of the board. It's supposed to be on this other axis, the z-axis, coming in and out of the board. There's a third axis. Yeah, what? Are you kidding me? You don't know that? How many dimensions of space do you live in? 3 dimensions of space. You're not a whiteboard, dog. You don't only have left and right and up and down. You have a third dimension. You can go all around. You can go forward and back, can't you? Did you not know about 3 dimensions of space before? There's a 4th dimension of, what is it? That we live in all the time, that we're just wandering through. Time. No, there's 3 dimensions of space and 1 of time. Is that what we can perceive? Anyway, so this third dimension, z, this would be coming in and out of the board. There's a better diagram on page 42 for FIA, but also in your the literal first picture in your explorations is an expression of this, that 90-degree angle between, which way is the energy moving, by the way? Right. Yep, right. We could say it's moving right. And this is the x-axis. So the energy is moving along the x-axis, and the waves, both the electric, the y-axis, and the magnetic, the z-axis, are both perpendicular to this movement of the energy. They're both transverse waves, and they overlap. And guess what? There are all different kinds of electromagnetic waves. When we say light, we usually mean what? Which very tiny part of the electromagnetic spectrum do we mean, usually?
Sunlight.
Yeah, which we can see, and so we therefore call it
Visible light.
visible light is what we usually mean, but that's only a tiny little portion. Let's diagram the electromagnetic spectrum now. What's a spectrum?
Like all the different kinds of light.
That's all the different kinds of light waves. Yep. In general, a spectrum is a range of values. For instance, we might say that there's a spectrum of student achievement in this class. We have very low achieving students and we have very high achieving students. And there's a spectrum, meaning there's a continuous function of them. Right about in the very middle of the electromagnetic spectrum, we have the rainbow. Where's my purple? I don't have a purple. Okay, we're going to pretend that the brown is purple. This is going to be a beautiful rainbow. We're going to pretend that the brown is purple. Purple has the highest. We're going to label these in a sec. Well, actually, let's label them now. As we move this way on our spectrum here, we get increased frequency, nu. Increase in frequency. More faster waves. We could draw it kind of like this. Low frequency down here, high frequency up here. Noticing about this equation, if I had a great big frequency, like down here, if this has to stay the same, which it does, this has to stay the same. If I had a great big frequency like I do over here, a great big wavelength like I do over here, what must be true of the frequency? Well, if this number is great big, let's say these have to multiply together to make 100. If I have a wavelength of 100, what must my frequency be? 1. It must be very low. They have to multiply to 100. What if I have a very, very, very low wavelength? Let's say my wavelength now is 0.5. What must my frequency be? 200. I must have a very high frequency. These two things are, like our CCC says, these two things are inversely proportional. As one goes up, the other goes down. So here with high frequency, we have low wavelength, and here with high wavelength, we have low frequency. Anyway, so here's purple, which has the highest frequency of all the visible light. Lower frequency than purple is blue. Lower frequency than blue is green. Lower frequency than green is yellow. Lower frequency than yellow is orange. And then red has the lowest frequency of all. What also is true of red? If what I just said is true, what also is true of red? Not only does it have the lowest frequency, it has the longest wavelength. And purple must have the shortest wavelength. But that's just the light we can see. And do we see these things because they're all emitting their, like, when I look at, we're going to call Peyton's shirt red. It's not really quite, but we're going to say Peyton's shirt is red. When I look at Peyton's shirt that's red, is it because it's emitting red light into my eyeballs like a laser beam?
Nope.
No, it's It's reflecting the red light. It's absorbing all these other colors of light, and it's reflecting red light, which I then see. But do you think it's only reflecting and absorbing visible light? No, there's below and above this invisible light. The rest is, so if this is visible light, the rest of it is invisible. What is the invisible light that has a lower frequency than what we can see?
Radio waves.
No. Yes, that's way down here though.
Microwave.
No. Infrared. Yeah, some people call them heat waves. That's not I don't think that's a very precise terminology, so we're going to call them infrared. You've heard of like infrared goggles. Those are goggles that can see effectively heat radiation. Infrared. Below infrared, someone already said it,
Radio
microwaves. And then below that, when I say below, I mean lower in frequency, radio waves.
Yay.
Radio waves have the longest wavelength and the lowest frequency. Okay, if we go above, by the way, the Greek word or the Greek prefix infra means below. So infrared, below red. If I go above brown here, but I mean purple, guess. If we had below red, we probably also have above, which we would say in Greek, you already know what it is. You've heard of this, I know you have. Ultraviolet, yeah. Ultraviolet. Or UV. Ultraviolet. Above that we have,
Gamma rays.
no, X-rays, and above that we have
Gamma rays.
gamma rays. What's true of all three of these?
They're higher. Holding the whole.
I said true.
They're higher in.
They're higher in frequency. They're also higher in energy. What is true of all these is that they make up some of the kinds of ionizing radiation. These have enough energy that if they interact with your skin or any other part of your body, they can knock off chunks of your DNA, which can cause cell death, mutations, cancer, that kind of thing. And so these are all ionizing radiation. These are dangerous. What happens if you get ultraviolet rays on you without any kind of protection? Do you die instantly? No. You get a sunburn because your skin cells die. That's right. Your skin cells die, and if you do it enough, maybe if you only do it once, but if you prolong that exposure, you have a higher chance of getting skin cancer. That's what ultraviolet rays, because they are ionizing radiation, because they have a higher energy than visible light. So looking at this, do you think it's reasonable? So we know this kind of stuff can cause cell death and mutations. X-rays, have you ever gotten an X-ray? Raise your hand if you've gotten an X-ray. What are the precautions that are taken when you get an X-ray? First of all, where does the lady giving you the X-ray go? She does not hang out with you. She's like, see ya, and she scurries off into another room because it's dangerous. What do they do to you, though? What do you get? They get a blanket where? No, not usually. Where? Why? Why here? Why? Why them, Tegan? Yeah, why, though? That's a cute thought, Lucas. No. What? What did you say? No, it doesn't. It wouldn't change your gender. So that you stay. Yeah, okay. 2 reasons. One, if the X-rays interact with your reproductive cells, your eggs or sperm, those can get mutations and either die or can damage the organs that produce those things, which means you could go sterile, which means you wouldn't be able to have babies. Or, since those are your reproductive organs and the reproductive cells, if you then did have, let's say one of them mutated, you had a mutated egg or a mutated sperm because of this, and then when you do have a baby, the baby could be born with mutations. And since the baby, as we talked about in a couple, would you knock it off for a second? Since the baby starts out as only one egg and one sperm, if that one egg or that one sperm is mutated, the entire genetic code of that baby is wrong, because it's only based on the genetic information of those. And so you get your reproductive organs covered when you do this, so that kind of thing doesn't happen, so it doesn't cause birth defects or sterility. And then these we almost never, ever, ever interact with. They're extremely dangerous. Some kinds of radioactive isotopes emit gamma radiation, although it's somewhat rare. But some kinds of radioactive isotopes emit gamma radiation. Stars emit gamma radiation. But these things, in addition to being extremely dangerous, are also absorbed pretty rapidly because of their high frequency. So as these things, which are all emitted by the sun to some degree, come into the atmosphere, these are mostly absorbed, stopping about there. Is this dangerous?
No.
No, not at all. How do we know? Is there evidence that this isn't dangerous? People, not just people, but critters have been seeing visible light as long as there have been organisms. And there have never been any dangerous side effects, except for, as you know, if you look at a really bright light, you go blind, either temporarily or long term. But this does not pose a danger. So then when people say, oh, the 5G is going to make my brain into scrambled eggs, or they say, oh, the radio waves going through you because of your Wi-Fi router are going to make you into a lunatic. Are these things dangerous? No, because what makes an electromagnetic wave dangerous is its frequency. And this that you see has a higher frequency than these things that people worry about. There's no danger with those things. A minor exception is that at some very specific frequency in here, I don't know exactly where, but at some very specific frequency here is the resonant frequency of water molecules. And so those the water molecules, when they absorb this exact frequency of radiation, they start to move a lot faster, which makes stuff heat up. This is how microwave ovens work. So the microwave oven has a little thing that emits this specific frequency of electromagnetic radiation. It makes the water in any substance heat up, and that makes the thing heat up. So you get your microwave burrito, and it comes out frozen. There's still water in it, but it's frozen water. You put it in the microwave. The microwave heats up those water molecules, and the burrito heats up. You wouldn't want to have your hand in there because you're also made of water. So there's a minor exception at some little range in here in the microwave range, which is why we have microwave ovens. But other than that, all of this stuff is by definition safe, or at least safer than visible light, which we all agree is safe. We will have probably time to watch. I want to show you a little video about these different kinds of light. But do you have questions so far about any of this? What kind of wave is light? Electromagnetic. Oh, and by the way, we talked about wavelength and frequency. What was the other property that all waves have? Amplitude. So the wavelength and frequency of light are what kind of light it is, or within the visible light, what color it is. But the amplitude is what the light is. Can you guess? How bright it is. Greater electromagnetic radiation amplitude means a brighter or a more intense light. Okay.